everyone and welcome back to R&M LAB. Today I'm presenting a prototype of a compact oscilloscope built with the ESP32. We've seen this board in a previous video where we installed an external Wi-Fi antenna. I'll leave the link in the description if you want to check that out. The ESP32 is an extremely versatile board and it's much more powerful than a standard Arduino. It features integrated Wi-Fi and Bluetooth, along with more memory and faster processing speeds, making it ideal for advanced projects like this one. I needed to read some signals for a project I'm finishing up, so I decided to run this experiment. I wanted to see if a prototype like this could be useful and accurate enough for real-world use. Since this is a first test, I'm quite satisfied. For a tool built in such a simple way, it has provided excellent results. Obviously, we can't compare it to a professional benchtop oscilloscope, but for quick measurements and visualizing waveforms, it does the job perfectly. Not everyone has an oscilloscope in their laboratory, and this is a great little solution that can really help out. For this project, I used an ESP32 board, a 2.8-inch TFT LCD display shield, 3 physical push buttons, 2 100 kilo ohm resistors and 2 10 kilo ohm resistors, jumper wires and a breadboard that I modified and split in two to properly house the board. The connections are very simple. You can find the full schematic in the link in the description if you'd like to replicate the project or just test its potential. It's a truly interesting experiment.
As you've seen, since this is just a prototype, the connections in this project are made entirely with jumper wires, with no soldering required.
My goal is to test it thoroughly and look for ways to improve it before moving to a final version. In the future, I plan to build a complete project, including a custom enclosure and proper measurement probes. For this prototype, I'm using 2 simple jumper wires to pick up the signals. Even though the signal isn't perfectly clean, it works well as an initial test. It allows me to take measurements that I can later compare with more professional instruments to check its accuracy. Now, let's move to the PC. Connect the USB cable and prepare our ESP32 board. For this project, make sure your Arduino IDE is updated with a dedicated ESP32 core, installing all the necessary libraries and versions. Once the environment is set up, select the correct board and the communication port. Now, let's upload the code. As always, you can find it in the description link along with the wiring diagram. If you run into any issues or have questions regarding the IDE configuration for the ESP32, feel free to leave a comment. I'll be happy to provide some technical support. Once the upload is complete, we'll finally see our prototype oscilloscope in action on the bench. As you can clearly see in the video, the on-screen graphics have been meticulously designed to ensure a clean and professional user interface. A key feature that sets this project apart is that it is a dual-trace oscilloscope. It can handle an input range from 0 all the way up to 30 volts, which is quite impressive for a DIY device. The 2 separate channels are color-coded in yellow and red, allowing us to monitor and compare 2 different signals simultaneously on the same screen. At the top of the display, the system provides a real-time digital readout of the exact voltage being detected by the probes. To manage the waveform visualization, I have integrated 3 physical buttons with specific control functions. The first button adjusts the time base, ranging from 0 to 100 milliseconds, allowing us to adapt the scan speed to the frequency of the signal. The second button changes the scale per division, giving us the ability to zoom in or out on the waveform for a more detailed view. The third button triggers the hold function. This freezes the current frame, which is essential when you need to stop and analyze a specific part of the signal without it scrolling away. For the live demonstration, we are going to test the readings using 2 different batteries, a single cell and a dual configuration. We'll observe both the digital voltage value and the linear reference line on the display. I have personally benchmarked this prototype against a professional-grade multimeter, and the accuracy is remarkably high. The deviation is only a few millivolts, a margin of error that is more than acceptable for a custom-built laboratory tool. Finally, we will push the prototype further by analyzing a square wave and other modulated signals. We will play with the sampling rates using the buttons to see how the display reacts to different frequencies. These test signals are coming from another one of my past projects, a custom function generator built with an Arduino. If you find this generator interesting and would like to see how it was made, please let me know in the comments. I would be glad to create a dedicated video for it, as it's another indispensable tool for any electronics laboratory. hope you enjoyed this video and found it useful for your future projects. If you're interested in the work we're doing here at the laboratory, don't forget to leave a comment, subscribe to the channel, and hit the notification bell. That's the best way to stay updated on upcoming videos and the new technological developments we have in store. Please share this video with your fellow electronics enthusiasts, as every share helps our lab reach more people. As I mentioned earlier, if you're curious about how I built the Arduino-based signal generator, let me know in the comments. If there's enough interest, I'll create a dedicated video from scratch, covering both the code and the hardware so you can build your own custom function generator. Thank you so much for watching and for your continued support. I'll see you in the next video. Bye.